This is the AM-GM inequality, the most famous inequality in all of math. If you don't know this quality, you're in the right place because you really should learn it. If you know this inequality, you probably don't know how to prove this inequality. If you know how to prove this inequality, the way you know is most definitely very complicated because a sophisticated proof of this theorem is indeed very difficult. However, today I will guide you through the natural process of discovering this theorem yourself and, more importantly, proving it using a super simple technique that even a primary school pupil can understand. So let's go into this together. Now, before we start, we mentioned in the last lecture some proofs on problems related to exponentials and logarithms. If you're just not interested in exponentials or logarithms and you really just want to learn about inequalities, move ahead to the second part of this video. If you are not familiar with exponential or logarithmic functions, take a moment to check out the last video because I think it's really meaningful, and I would probably recommend you to think through these problems carefully before we start. The first problem requires for us to prove that any non-zero real-valued continuous function with this identity must be an exponential function. An exponential function essentially is a to the x power, where x is the variable. Let's try and prove this. So when we're analyzing functions that we do not know, but we have some identities around it, we can plug in special values. For instance, in this case, assume y is equal to 0. Then we have the identity fx times f0 is equal to f of x. That means f0 is always 1. This is the first identity. Because in case f0 is 0, then it is a 0 function. So since it is a non-zero function, f0 must be 1. Now, let's think about this intuitively. Assume we have the point 1, a on the graph of this function. So in this case, we note that the function g of x is equal to a to the x power passes through both the points 0, 1 here, and also 1, a. So here we are trying to prove that any function satisfying this identity must be equivalent to g of x. So we're trying to prove f of x is exactly g of x. And we have to plug in some special values again. F of x times f of x, assuming x is equal to y. In this case, it is equal to f of 2x. So given f of x, we can find f of 2x. Now note that g of x times g of x, which is equal to a of x times a of x, is equal to a to the x power squared, which is equal to a to the 2x power, which happens to equal to g of 2x. So the same identity holds for both functions. That means if we extend from x equals 0 and x equals 1, we can obtain x equals 2, 4, 8, etc. And all these points also lie on g of x because they have the same identity. Now, in turn, we can also say f of x is equal to the square root of f of 2x. And then since we have already the information about f of 1, that means we can go back and find f of 1/2, 1/4, etc. So we have a large amount of points already. Now, we can go one step further and see if we can find the midpoint of any two x values. For instance, suppose the graph looks something like this. Given these two values, we want to find this point. If we can do so, then that means we can find every value on the graph because essentially you're just cutting a segment down by 1/2 each time, and that just covers every single possible point. In this case, given the identity we already have, we know f of x times f of y is equal to f of x plus y, and we also know f of x plus y divided by 2 squared is also equal to f of x plus y. So given x and y, we can find this. And simultaneously, this holds true for g as well. So again, whenever we obtain a new point on f, it is also on g. So f and g are the same functions. And that means, given the information for 0, 1, and 1, a, and also this identity, there is a unique function, and this function happens to be the exponential function. Similarly, we can do the same for logarithms. However, this time, I really want to show another less intuitive way of proving it. However, this proof is much more rigorous. To begin with, we will again use the property by applying x equals y. We have 2 fx is equal to f of x squared. So now we're going to apply a step that is less intuitive, which is we define g of x is equal to f of e to the x degree. Then in this case, let g of x plus y, we know that it is equal to f to e to the x plus y power. And this is essentially equal to f to the e of x power plus f of e to the y power. And this is g of x plus g of y. Now, after that, we only need to prove that g of x is exactly equal to x, or perhaps a constant x, because in that case, we can derive easily, since f of e to the x degree is equal to a constant value times x, we have f of x is simply c times ln of x. And then in that case, our theorem is proven. So the inspiration here came from the fact that we know by experience g of x plus y is gx plus g only when gx is equal to a constant times x. And as for the proof of why this is true, you can first of all try yourself, and then if you get stuck, you can check the materials in the description, get the document, and I gave a detailed proof of this lemma there. And now it's high time we move on to the third problem. And if you did solve this problem, I think you're really talented, because this is one of those classic examples where you are actually solving a decently hard problem purely from problem solving rather than experience, because this is one of those very ad hoc problems. So let's try this ourselves. We already know e is equal to the limit of n to infinity of 1 plus 1 over n to the nth power. And now we want to prove that e of e to the tth power is exactly this statement by changing 1 to t. Well, how can we do this? First of all, we can try to just plug in the t here. E to the tth degree is equal to the limit of n to infinity of 1 plus 1 over n to the nth degree, and then take the t outside of it. And then essentially what we want to do here is somehow make the exponent here n rather than n times t. How then is that possible? Before we begin, let us just try to substitute n to some other value. Let it be m. Boom. In this case, suppose m times t is equal to n. Well, m and n are both approaching infinity, so this is always true. Any multiple of infinity is simply infinity again. So in this case, essentially nothing changed. Inside it is still e, it still holds true because m is still infinity. However, under this circumstance, we note that suppose m times t is equal to n. Then what is m? M is n over t. Now we can plug this back in. The limit of n over t to infinity of 1 plus 1 over n over t, which just happens to be t over n, that is the target equation, to the t over nth degree entirely to the tth power. And as we already know, this is in fact equal to e of t. So of course here we can't claim it is equal to e of t yet, but after some manipulation to this formula by substituting m into n, and then plugging in m equals n over t, we obtain the target equation. Because this equation in the middle, even though it doesn't look the same, it is still the same thing because we're taking the limit. Infinity divided by a constant value, of course, is still infinite. So we have proven it is in fact e to the t. Very interesting. Now, we have finally finished the talk about homework, and now we're back to inequalities. In this lesson, we're talking about advanced inequalities, the most famous of which is AM-GM. I will be also explaining the Cauchy inequality and its extended lemma of angel form or Titut's lemma. What is inequalities in this case referring to? It is something that is always true, given a realm of definition. For instance, for a squared is greater than 0, we give the realm that a is real. Then this thing always holds true. Similarly, in this case above here, the constraints are that x1 to xn must be positive. Or you can also include one of those values. It can be 0, but when it is 0, it is degenerate because the right side is 0 and the left side is positive. Now, let's dive into how mathematicians first discovered this and why it is true. Whenever we want to claim something is true for n terms, let's focus first on 1 or 2 terms. In this case, studying a itself doesn't mean much. There doesn't seem to be anything interesting about 1 term. So let's focus on 2 terms. Let that be x and y. Well, we know we have a number of equations just based on a squared is greater or equal to 0, including these two, which just seems the most natural 2 expressions. Note that for the first case, equality occurs when x is equal to negative y, and equality occurs when x equals y for the second equation. In this case, we want something interesting. For instance, we have x squared plus y squared is then greater than 2xy from the second expression. Now this thing is already quite meaningful because for any x and y, this thing holds true, and equality only occurs when x is equal to y. This is already an inequality in itself, but let's go one step further and make this thing cleaner, which is substituting x equals square root of a, y equals square root of b. This gets rid of this second degree sign nicely, and it gives us a plus b is greater than 2 times square root of a times b, and in that case, we can move the 2 down here. So in fact, the left side is the arithmetic mean of the two numbers, and the right side is the geometric mean of the two numbers. And when does equality occurs again? You might recall, since we're claiming equality occurs when x equals y, in this case a is equal to b then. In fact, it is equal, the left side and the right side. So this equation has two layers of meanings. The first layer is that there is a lower bound, the sum of two numbers. And also the second layer of meaning is that there is an upper bound to the product of two numbers, given the other thing stays the same. Since it is easier to keep a plus b the same, because sums are generally easier to deal with compared to multiplication, then we can analyze what happens when we assume a plus b has the constant sum, and what happens when we change a and b, what happens to their product. Well, given two numbers x and y, what is the most natural thing that can change to these guys, even though we maintain s is equal to x plus y and f does not change? I think the most natural thing here is taking the midpoint. So we can change these values both to x plus y over 2. What happens to their product then? Remember, their product originally was x times y, and now it is x plus y over 2 squared. And this is x squared plus 2xy plus y squared over 4. Let's check out the difference of before and after. The difference is x squared plus 2xy minus y squared over 4 minus x times y, or it can also be written minus 4xy over 4, so the entire equation is equal to 4 under x minus y squared. And again, we know this thing, it is greater than 0. So no matter what, when we apply this operation, x times y is going to increase. So this is a really important thing. We can conclude it to the following statement. For two values with a constant sum, smoothing them out or making them closer to each other increases their product. That is very useful information because now we can extend to an n-term case. When we study n-terms, let's imagine that n-terms as values on sliders. We are just dealing with 4 values. However, these 4 values, they have a constant sum. Or by extension, it also has a constant mean. So this is the constant arithmetic mean. Let's just assume this arithmetic mean has a line on these sliders which locates somewhere around here. Let's assume this is the arithmetic mean. What happens to these numbers? First, we focus on the two numbers that are furthest from each other. We take their average. So after that, the two dots move over here. Now they're the same value. Then we do the same thing again. We focus on this pair, and suppose they move onto the arithmetic mean. We focus on this pair as well, and then they move onto the line as well. So we also know, since each time we're smoothing them out, so the product is always increasing. When all points are on the mean line, then it cannot be increased further. So when every single value is the same, the product reaches its upper bound. So essentially what I'm doing here is, given that the sum of x is consistent, we repeat the process by taking the maximum value and the minimum value, and we take their midpoint. So we repeat this process until x1 is equal to everything and is equal to xn is n overall is equal to s over n. And this must be achievable because every single step we are decreasing their difference, and at some point, even if it is infinitely many moves, at one point it must close down onto the line. Every single step we're getting better and better, so every single step we are closing down on the upper bound. What is the upper bound exactly? Which is the product of all these x values. It is equal to s divided by n to the nth power. This is the upper bound. So that means the product of the x values is lesser or equal to s over n. We move this power over here to give it to the root, and then this is the geometric mean. This is also the arithmetic mean. So these two values are the same, and we have successfully proven it by using this process of smoothing out the values until it is the same, and always increasing the product until it's upper bound. We are done. We have successfully proven the famous AM-GM inequality. So AM-GM is a complicated inequality, and I admit it is something quite interesting and something quite hard. So some problems related to AM-GM can be quite difficult, but let's dive into it carefully, and I'm going to first give you a few examples so you can have a better understanding of it, and then we'll try some problems. So before we tackle this problem, let's review what is happening. So given a constant sum, then the product has a maximum. Given a constant product, the sum has a minimum. So when you come across optimization problems and you see it's asking for the maximum value, try to construct a product which has a constant sum. When you come across minimum values, try to construct a sum with a constant product. For instance, for the second example here, if I ask you what is the minimum value for this when x is greater than 0? And a quick note on why it must be greater than 0 and GM to be true. The reason is you have a square root here. That means if the thing inside is negative and you're applying a square root to it, it's going to be disaster. But if we just don't try to write this so beautifully as AM-GM form, but we move the square root symbol over here to the power over there, then it naturally is then true, because our reasoning process just implies that it is indeed true. So AM-GM is a powerful thing that can spread across all real numbers. However, it depends on how you write it. Back to this example, where x is greater than 0, because generally, in my opinion, if you allow x to be real, things get messy. But if you don't, it becomes a lot cleaner because you don't have to worry about the signs. In this case, we're trying to construct a product that is constant because we're looking for the minimum value of this. Indeed, x times 1 over x is constant, it is 1. So the minimum value of the sum occurs when x is equal to 1 over x, or x is simply equal to 1. So the minimum value of this expression is 2. Now, something harder, something a little more disguised. Since we're looking for the maximum value, then we're trying to construct a product with a constant sum. See if you can find it yourself. The way to go here is you first look at the numerator. This thing really looks like a constant sum in a sense, because even though t is not technically constant, it is around constant, because when you add these parts up, it is in fact just simply equal to 2 to the t power. Then you're going to try to split this part, because the entire thing must be a product. Then you can write it as 2 to the t power minus 2 divided by 2t times 2 to the t times t over 2 to the t power. In this case, this thing has a constant sum, which happens to be 1. Exactly. So that means its maximum of the product occurs when 2 to the t power minus t over 2 to the t power is in fact equal to t over 2 to the t power. And in this case, we can solve for t. Essentially, 2 to the t power is equal to 2t, so t here then is equal to 2. Since t is equal to 2, we can plug that back in, and that is 1/2 times 1/2, which is 1 over 4. So the maximum value of this expression is 1 over 4 when t is equal to 2. Now, this is a simplified version of an AMC12 problem. Let's look at the full version. The full version has an extra 3 here. And since this is a late problem, I'm going to give it a difficulty of 3 or 4. The reason that I first thought about giving it 3 is because if you're very familiar with AM-GM, this is very obvious, but if you're not, it can be quite challenging. So try to solve it yourself. I hope you tried and succeeded, but if you didn't succeed, don't worry. Remember last time we constructed a constant sum. Then this time let's try the same thing again. Since this time we can't really add t to form a constant sum, so what do? We add 3t. We just multiply a 3 to the entire expression and then multiply it by 1 over 3 as well. So after that, we can follow the same problem-solving process by applying these two terms, AM-GM, and you arrive at the conclusion over here. The maximum is again 1 over 4. So the maximum of the entire expression is 1 over 3 times 1 over 4. 1 over 12, and we are done. Next problem. This one is actually a problem that I promised you a long time ago. In the second video, I said we're going to have some more interesting problems related to solvability, and this is one of those examples. How many ordered pairs of positive real numbers A, B satisfy the equation? Of course, it is positive, so you can use AM-GM freely. How many of them do satisfy this thing? Check it out. If you said 1, congratulations, you are correct. Why? Let's analyze it together. First of all, you notice that you can remove a 2 out of this thing, so why don't we do that? Now, we can apply AM-GM to the terms 1, 2a, and b. What happens is 1 plus 2, it is greater or equal to square root of 2a. 1 plus b is greater or equal to square root of b, and 2a plus 1 is greater or equal to 2ab. Of course, there's a divide 2, I forgot to write that. And that means this product is greater or equal to 16ab if you combine everything together. And you notice that these two things are exactly the same. So that means we are trying to locate when we can take the equal sign. And that is when 1 is equal to 2a and is equal to b, which is a equals 1 over 2, b equals 1. And this is the unique solution. This is the only thing in the real realm that satisfies the equation. And we're done. Again, even though it is from problem 23, because AMC12 really think inequalities are a hard topic, so they're putting a lot of these AM-GM problems to the last few questions of each test. However, again, I don't think this is difficult if you're very familiar with AM-GM. So difficulty 3 again. Now we have seen 2 problems related with AM-GM, and I hope you have a better understanding. Now let me show you another inequality that is even rarer in AMC12, but is still very important and still a thing of beauty, which is called the Cauchy inequality. Remember, last time we began with x minus y squared is greater or equal to 0. This time, let's do something similar. Let's treat the 2 terms as a linear expression, like this. So in this case, a and b are constants, and x is the variable. Similarly, from here, since ax minus b squared is greater or equal to 0, we can expand the left side. A squared x squared minus 2ab plus b squared should be greater than 0. We also do know the determinant, which is 4a squared b squared, the square root of this term, minus 4a squared b squared, which is equal to 0. No luck. But something very interesting. Suppose we add these terms. Then in that case, it is actually the sum of a to the xth degree times 2 times the sum of a and the sum of b to the sum of b squared as the constant term. In this case, the determinant now is equal to 4 times the sum of a squared times the sum of b squared. This time the determinant is actually 4 times the sum of ab squared minus 4 times the sum of a squared times the sum of b squared. So more accurately, I should have written 2 times ab, sum of ab. The reason of which is because imagine adding up these terms. Like this is a1, b1, this is 2, b2. What happens when you expand them? What happens is you have a1 squared times a2 squared as the coefficient of the second degree, and then you also have 2a1b1 plus a2b2, and then finally b1 squared plus b2 squared. So here the terms are actually 1 by 1 corresponding. In this case, remember, the entire expression should be greater or equal to 0. So if we graph out this quadratic, it's going to look something, this is the x-axis, it is going to look something like this, because it is always greater than 0. What is the determinant in this sense? Of course, it can also go above, because all we are requiring that it is greater or equal to. It can also be greater. So that means the determinant is actually lesser or equal to 0. In that case, we can rewrite it as the sum of ab squared is less than the sum of a squared and the sum of b squared. And this thing actually always holds true because the originating expression is always true. This is the Cauchy-Schwarz inequality, or more commonly known as Cauchy inequality. For example, to give a better feel of this statement, we can take 2 terms, a1b1 and a2b2. In this case, we can treat b1, b2 as constant values. Then under that circumstance, we have a1 times b1 plus a2 times b2 squared is lesser or equal to a plus a1 squared plus a2 squared times b1 squared plus b2 squared. Recall that these terms are constant. So essentially, it builds a very classic looking bridge between two things added together versus the second degree of each term. For instance, if we simply let b1 equals b2, then we have a1 plus a2 squared is lesser or equal to a1 squared plus a2 squared multiplied by 2. This is what we can gain from the two-term version. Now, we mentioned there is also Engel form or Titut's lemma, which is a more commonly seen version of Cauchy-Schwarz, which is essentially, we're asking you to prove this. Prove that for positive real numbers a1, a2, all the way up to an, the following expression is true. So in this case, we're treating a as constant, and we're trying to link the relationships between x squared and the sum of x squared. That is essentially something similar to what we just saw, the two-term version of Cauchy. But let's go one step further and prove it for the n-term version. At first, it isn't obvious, but let's do some manipulation. The equation here can be written as a product version, because the Cauchy original version is a product version, so we should better write it as product. It looks like this. Now let's try term-to-term correspondence. Since the variables here are a bit conflicting, let's first change all the a up here to c, which looks like this. So we're trying to apply term-to-term correspondence, so we know that, in theory, x should be equal to a times b. And then we also know that c should be equal to a squared. And then x squared over c should be equal to b squared. And this makes sense because, essentially, if we multiply these two things together, it's x squared is equal to a squared times b squared. So this correspondence works. Then what exactly are we applying? That means we are applying Cauchy to square root of c and x over square root of 3, square root of c, because essentially we are trying to remove the square root mark here. So a corresponds to square root of c, b corresponds to x over square root of c, and under this scenario, we can plug this into the Cauchy inequality, and it is proved. In fact, the statement, or it is written as Engel form or Titut's lemma, is true. And that concludes today's lesson. It isn't a long lesson, but inequalities are considered one of the hardest topics in AMC12. You have probably seen it just through how highly rated the problems are, even like this one, which to an experienced AM-GM user, one probably can solve this in 1 minute, but it's rated problem 22. So very important and very interesting topic as well. I hope the proof today really did inspire you, and the simple version of understanding complex things really helped. As a last thing, here's the homework. The first one is for your AM-GM practice, and the second one is actually you are revisiting this problem which you have seen before. Before I told you about how to solve it using graphing. This time try to solve it using Cauchy-Schwarz, because you notice there's a relationship with a and a squared. Finally, of course, it would be really nice if you can prove everything from AM-GM to Cauchy to Engel, prove them independently without watching this video. See if we can do it and understand everything better in this way. This concludes this video, and the day after tomorrow, we will be talking about one of the most interesting topics in algebra, and I'm super excited. So don't miss out tomorrow, and we'll have fun together. Bye!